A very good morning to all. I'm Pahari and I'll be presenting our work titled Modeling the Linear Rheology of Nanoparticle Enhanced Viscoelastic Fracturing Fluids. The presentation is divided into motivation and background, model formulation, results and discussion, conclusion, and future scope. Coming to the motivation and background, since the year 2017, hydrocarbon production in the United States has been driven by production from unconventional reservoirs. Owing to the production from these reservoirs in the year 2017 for the first time, the US became a major energy exporter. This success was possible with the help of technologies like hydraulic fracturing and horizontal drilling. Furthermore, owing to this success, the fraction of unconventional wells drilled and completed have significantly increased over the years from 2010 to 2019. Although hydraulic fracturing has contributed to one of the biggest revolutions in the history of US energy, some environmental concerns associated with it has been alarming. The biggest concern is over the use of large quantities of fresh water during the hydraulic fracturing operations. In spite of these challenges posed by hydraulic fracturing, it continues to play a key role in the energy scenario of the United States. A report prepared by the US Department of Energy in 2021 shows that restricting hydraulic fracturing can have significant impacts on the energy security and the economy of United States. However, since then, many new strategies have been adopted to meet these environmental challenges posed by hydraulic fracturing. In this regard, major research has been carried out in the domain of effective fracturing fluid design. Design of novel fracturing fluids that can reduce the water usage while minimizing formation damage and mitigating serious issues associated with poor flowback has been a very active area of research since 2018. In 2019, a novel viscoelastic complex fluid was designed, which had reasonably good elastic properties that allowed these gels to minimize water leak-off and also possess sufficiently low zero shear viscosity that allowed them to flow back easily. Specifically to enhance the viscosity of these gels, nanoparticles are utilized. It is to be noted that VES fluids are composed of worm-like micelles or WLMs. These WLMs get cross-linked with nanoparticles and these cross-linked fluids have significantly high viscosity. The VES fluids are synthesized under different reaction conditions, which provides a great degree of freedom for their design. In order to better understand the design heuristics of such materials, rheology models are required. Specifically, these models can aid us in exploring the properties of viscoelastic fracturing fluids and finally provide us the optimal concentration of nanoparticles that should be chosen for designing VES fluids with desired properties. Hence, mesoscopic models that can capture the rheology of VES fluids has been developed. Specifically, the relaxation dynamics of worm-like micelles alongside cross-linking of worm-like micelles by adsorption of nanoparticles has been considered in these models. Coming to the model formulation section, to model the rheology of WLM-based VES fluids, a slip spring framework was considered in this study. In this framework, the WLM chains are modeled by by beads which are connected with springs of harmonic potential. The entanglements of the between the WLMs are modeled via slip springs. These slip springs can slide past the WLM chains, which essentially mimic the dynamic nature of the entanglements present in the system. Kinetic Monte Carlo algorithm, which has successfully been applied to many studies related to polymer stress relaxation, is utilized here. Alongside relaxation dynamics, adsorption of worm-like micelles or nanoparticles has been considered in this framework. Specifically, adsorption of worm-like micelles or nanoparticles have been modeled with a separate KMC simulation. Finally, since the KMC simulation for relaxation dynamics and adsorption take place at a very different time scale, a novel integration strategy is implemented to integrate these simulations and predict the solution rheology. To model the relaxation dynamics, specifically, three KMC steps are implemented to capture three crucial mechanisms for stress relaxation of WLMs. The first KMC event is slip spring hopping event, where one end of the slip spring hops from one bead to the other. This mechanism mimics the primary stress relaxation process where WLM change disentangles itself from topological constraints via curvilinear diffusion. The second KMC event involves the creation and destruction of slip springs, where the slip springs are created and destroyed at the end of WLM chains. This physically mimics the mechanism of constraint release, where owing to the diffusion of WLM chains, its entanglements with the old chains are destroyed and entanglements with the new chains are created. Finally, the third KMC step models the mechanism of union secession, where the WLM chains break and recombine continuously. This is also a crucial mechanism for stress relaxation and is very unique to systems of WLMs. Once the crucial stress relaxation mechanisms are modeled effectively, KMC algorithm was implemented to model the adsorption of WLMs. KMC simulations to capture WLM adsorption on nanoparticle is executed at a very different time scale. To capture the impact of WLM adsorption on stress relaxation, a cross-linked bead is introduced. WLMs are connected to this bead by strong restraining harmonic potentials. This significantly increases the topological constraint imposed by the newly introduced bead in the simulation domain and thus leads to an increase in relaxation time and dynamic viscosity. Having defined and formulated the phenomenological processes underlying the stress relaxation of WLMs, mathematical expressions for the same are derived, which are highlighted in Table 1. As is highlighted in the table, the model has five crucial parameters, which are estimated by fitting the model predictions with experimental data. Furthermore, the green shaded portion of the table highlights the corresponding event for stress relaxation, while the yellow shaded portions highlights the events for adsorption and desorption respectively. Once the parameters and the rate expressions for the two KMC events are executed, a novel integration strategy is implemented. The integration strategy is highlighted in Figure 12. As is shown in Figure 12, the time steps for stress relaxation events is very small and is in the order of few nanoseconds, while the time step for adsorption event is in the order of few seconds. To implement these two simulations together, simply 10 index 10 relaxation events are performed one after the other between two consecutive adsorption events. After adsorption, when the stress relaxation calculations are performed, a cross-linked bead is introduced into the simulation domain. This introduction of cross-linked beads act as a connecting step between these two timescales. Once the model is developed, it is implemented to obtain results. And so we come to the results and discussion section. First, the developed model is implemented to observe the variation in the length distribution of the WLMs. This is essential because unlike conventional polymer-based systems, WLM-based systems have an exponential length distribution. This distribution is found to be preserved throughout the process of stress relaxation from experimental studies. To check how effectively the living nature of WLMs are modeled in the proposed framework, the population distribution are observed before and after the stress relaxation simulations. For an ensemble of WLMs with a mean length of 1200 nanometer, the WLM length distribution is found to stay preserved at the end of relaxation process. Furthermore, the mean length of the ensemble also remains the same. This is in great agreement with experimental results, which highlight that the mean length and the length distribution of WLM stays the same throughout the relaxation process. Thus, this shows that the living nature of WLMs have been captured in an accurate fashion, and thus the model can be further used for further analysis. Furthermore, to gain more fidelity model predictions were validated with experimental results. Specifically, a system of WLMs composed of CTAB, sodium salicylate, and 0.38% silicon nanoparticles at 25 degrees Celsius has been chosen. The model predictions were found to be in good agreement with the experimental results, and they are highlighted in Figure 15. The normalized root mean square error is found to be 7%. And thus, owing to this fidelity, the developed model was further used for predicting the rheology. Once the fidelity of the model is confirmed from the experimental finding, it was used to predict the rheology for different silicon nanoparticle concentrations. It is found that on increasing the silicon nanoparticle concentration, the crossover frequency decreases significantly. This implies that the zero shear viscosity increases on increasing the silicon nanoparticle concentration, which again implies that on increasing the nanoparticle concentration, there would be the tendency to flow back would reduce. While on the other hand, we observe that the plateau modulus remains almost the same on increasing the silicon nanoparticle concentration. This again indicates that there has been no significant gain in the elastic properties of the WLMs on increasing silicon nanoparticles. Hence, in this case, sticking with 0.38% silicon nanoparticles would be a good option because it would allow easier flowback of the fracturing fluids after hydraulic fracturing operation. Moving on a very similar note, when the analysis of 0.38% silicon nanoparticle is done with 0.08% silicon nanoparticles, it is found that the plateau modulus has gone down significantly, while the crossover frequency remains almost the same. This indicates that on reducing the silicon nanoparticles, the tendency to flow back remains almost the same, whereas the elastic properties of the gels have significantly reduced. This again means that silicon nanoparticle 0.08% silicon nanoparticle based West fluids would not effectively reduce the water consumption significantly, and hence in this case we should prefer to use a 0.38% silicon nanoparticle based West fluids. On this similar fashion, multiple analyses can be done and the rheology for different nanoparticle concentrations can be predicted. So coming to the conclusion and future scope, here we have developed a mesoscopic model which predicts the rheology of WLM based West fluids cross-linked with nanoparticles. The model predictions are in good agreement with experimental data, and the developed model can be used to find the optimal nanoparticle concentration that would give us the viscoelastic surfactant based fluids for particular operations. At the same time, this model can be extended to predict the nonlinear rheology behavior of the WLM solutions as well. And uh, these nonlinear rheology would become very significant when predicting fluid flowback and formation damage very accurately. With this, I would like to conclude the presentation and extend our appreciation to the funding agencies. And also, I would like to extend my appreciation to my advisor, Professor Khan, who has been a source of motivation and support in this project throughout. Finally, these are the references that we have cited, and thank you, and I'll be happy to take any questions.